Show by the principle of mathematical induction that for all n belonging to the set of natural number, the following is true. Okay, let us begin. So here, first what we'll do, we're going to consider a statement. So we're going to name the statement as P of n. So let P of n be the statement which is going to be given by. Now our goal will be to verify that this particular statement is true for all natural numbers. So what we'll do, we'll start with the first natural number, n equals to 1. All we have to do is replace n with 1. Now when we replace n with 1, so what we'll be getting here is only the first term, so that's 1 divided by 1 multiplied to 3. So that's going to be equals to, we'll substitute the n value with 1 on the right hand side, where 1 divided by 2 plus 1. Now 1 over 1 times 3, that's simply 1/3. This is also going to be equals to 1 over 3. So this only tells us that P of 1, or we can say this implies that the statement P of n is true. It comes out to be true if we choose n to be equals to 1. So that's the first step. Now that we have shown that it's true for n equals to 1, we will suppose that the statement P of m is also true. It is true. So if P of m is true, all we have to do is take this particular statement and we're going to replace n with m. This is going to give us, now that we have the statement P of m, where m is some natural number. So we have to specify that m belongs to the set of natural numbers. Our goal will be to show that this particular statement also holds true if we take the next consecutive natural number of m. So after m, we have m plus 1. So we know we need to show that P of m plus 1 is also true. It is also true, which means that we need to show that P of m plus 1, so this is going to be, we'll take the first term, which is 1 over 1 times 3, added to the second terms 1 over 3 times 5, going all the way up to 1 over 2m minus 1 multiplied to 2m plus 1. Now, what we'll have to do is we'll have to substitute this m value with m plus 1. That's going to give us 1 over, so we have 2 times m plus 1 minus 1. This is going to get multiplied to 2 times m plus 1 added to 1. Fine. Okay, so this is going to be equals to m plus 1 divided by 2 times m plus 1 added to 1. Fine. So here, this is what we need to show, that this is true. Now, how do we show that this is true? So what we'll do, we'll start with the left hand side of Pm plus 1. Now, in the left hand side of Pm plus 1, so let's write down, we have 1 over 1 times 3, added to 1 over 3 times 5, going all the way up to 1 over 2m minus 1 multiplied to 2 times m plus 1. Fine. Added to 1 over. So here we have, once we simplify this, we're going to get 2 times m added to 1. This is going to get multiplied to 2 times m plus 3. Fine. Okay. Now, from the first term all the way up to the last term, this is nothing but P of m. The statement P of m, the left hand side of the statement P of m. We know that's equals to m over 2m plus 1. Now, this is going to be equals to m over 2m plus 1 added to 1 over 2m plus 1 multiplied to 2 times m plus 3. So we're going to combine these two terms, and this must be equals to m plus 1 over 2 times m plus 1 plus 2. So let's verify that. So here we will combine them by taking the common denominator. So that's going to be 2 times m plus 1 multiplied to 2 times m plus 3. Fine. Then in the numerator, we have m times 2 times m plus 3 added to 1. So when we simplify this, the numerator now is going to give us 2m squared added to 3 times m added to 1 whole divided by 2 times m plus 1 multiplied to 2 times m plus 3. Fine. So this is going to be equals to, now what is 2m squared plus 3m plus 1? So we can factorize the numerator portion. So that's going to give us m plus 1 multiplied to 2 times m plus 1 whole divided by 2 times m plus 1 multiplied to 2 times m plus 3. So we can factor out 2 times m plus 1 from the numerator and the denominator, and this is going to be equals to m plus 1 divided by 2m plus 3. However, we can rewrite it as 2 times m plus 1 added to 1. And this is exactly the expression on the right hand side, which means that we have shown that p of m plus 1, this particular statement is true. So if p of m plus 1 is true, then we can now generalize it and we can say that hence p of n is true. This is a true statement for all n values belonging to the set of natural numbers. So here we have used the principle of mathematical induction to prove our problem.